Have you ever thought about our planet's finances? Not with money, but with something way more fundamental, energy. You see, the Earth has a budget, a really delicate balance of energy coming in and energy going out. And this budget, it dictates literally everything, from a sunny day to the future of our climate. So let's break down how it all works.
So I know what you're thinking. A budget. Is that just a nice metaphor, or does our planet really have to account for every little bit of energy that comes in and goes out?
Oh, it absolutely does. It's a real thing. Scientists call it the surface energy balance. And just like your own budget, it's all about balancing the income with the expenses. This constant flow, this balancing act, is the engine that drives our weather, our water cycles, and basically life as we know it.
All right, so let's get into the fundamentals. Let's see how this whole planetary accounting system really works.
At its heart, the surface energy balance is just that, an accounting system. It's how we keep track of all the heat, all the energy that's moving between the ground we're standing on, the air above us, and the soil beneath our feet. So how does all this energy actually move around? Well, it happens in three main ways. First up is radiation. That's energy traveling as waves, like the warmth you feel from the sun. Then there's conduction, which is heat transfer from direct touch, like when a hot sidewalk heats up your shoes. And finally, convection. That's heat moving through fluids, like when you see heat shimmering up from that same hot pavement. Okay, so we've got the rules of how energy moves. Now let's look at the biggest line item on the income side of the budget, all that energy coming to us from the sun.
Now, the radiation in our budget comes in two main flavors. The income is high-energy shortwave radiation that comes from the super-hot sun. The expense is the lower-energy long-wave radiation that our much cooler Earth sends back out. So shortwave in, long-wave out. Remember that, because this distinction is absolutely critical.
And here's why that difference is so important. It all comes down to temperature. Hotter things, like the sun, blast out energy in shorter, more powerful waves, like visible light. Cooler things, like our planet, give off energy in longer, less intense waves, mostly as infrared heat. You can't see it, but you can definitely feel it.
But here's something that might surprise you. Not all of the sun's energy actually gets deposited into the Earth's bank account. Get this, only about half, just 53%, of the sun's energy ever makes it to the surface. A huge chunk of it gets bounced right back into space by clouds in the atmosphere before it even gets here.
This whole idea of reflectivity has a name, albedo. Think of it like this, wearing a white shirt versus a black shirt on a sunny day. A surface with high albedo, like bright white snow, reflects a ton of sunlight and stays cool. A surface with low albedo, like dark, wet soil, absorbs that energy and heats up. Albedo is a huge factor in deciding how much solar income gets accepted versus how much gets rejected.
Okay, so that's the income side of the equation. Now let's flip the ledger over and look at the expenses. What does the Earth actually do with all the energy it absorbs to keep that budget balanced?
It all boils down to this really elegant little equation. Don't worry, it's simpler than it looks. Rn is net radiation. That's your net income. And that income has to be spent in three main ways: G, H, and LE. The income has to equal the expenses. The budget always has to balance.
And you can see this budget play out over a single 24-hour cycle. During the day, the income is pouring in from the sun, and the surface is busy spending it, heating the ground, warming the air, and evaporating water. But then, at night, the income stream shuts off completely. The budget flips. Now, the surface is only spending, radiating heat away into space and cooling down.
So what exactly are those three expenses? Well, G is for the ground. It's the energy that gets stored in the soil. H is for sensible heat. That's the energy that warms up the air around us, the heat you can actually feel. And LA is latent heat. Now this one is kind of the secret weapon. It's the energy used to evaporate water. It's basically the planet's air conditioning system. Evaporation is a powerful cooling process for the surface, just like sweating cools you down.
So for thousands and thousands of years, this planetary budget stayed remarkably stable. But what happens when you start messing with the accounting? That brings us to maybe the most critical topic of all. What happens when the budget is forced out of balance?
And this isn't a side issue. The source material puts it very directly. Changes in the Earth's radiation balance are a central issue in climate change. It's not a symptom, it's the core of the whole thing.
And these two charts, right next to each other, tell the story of our time. On the right, you see the relentless, steep climb of carbon dioxide in the atmosphere. And on the left, almost a perfect mirror, is the rise in global average temperatures. You can't deny that correlation.
So how does one cause the other?
How does this throw the whole budget out of whack? Well, remember that long-wave radiation, the expense the Earth pays to cool itself off. Greenhouse gases, like CO2, act like a sort of blanket in the atmosphere. They absorb some of that outgoing heat, trapping it and preventing it from escaping to space. So in budget terms, they're making it harder for the planet to pay its energy debts. This creates a surplus, and that energy surplus is what we call global warming.
And what's the result of that surplus so far?
Well, the data shows about a 1.25 degrees Celsius increase in the Earth's average surface temperature since 1900. Now, that might not sound like a huge number, but for a budget the size of an entire planet, that represents a massive, and really consequential imbalance.
Okay, the global picture is daunting, for sure, but understanding this budget gives us some really cool insights. It shows us that we don't just affect the system by accident on a global scale. We can actually manipulate it on purpose on a local scale, acting like energy accountants to get specific results.
Yeah, just by changing what the ground looks like, we can completely rewrite the local energy budget. And a perfect real-world example of this is a land management tool that's been used for a long time, the controlled burning of prairie grasslands.
Just look at this data. It's comparing a burned patch of prairie to an unburned patch right next to it. Check out that first line, net radiation. After the burn, the ground is much darker, right? So its albedo goes way down, and boom, its energy income skyrockets. But now, look at how it spends that extra income. Way more energy goes into evaporation, that's latent heat, and way less goes into just heating the air, the sensible heat. By doing one thing, we've completely re-engineered the local climate, all by hacking the energy budget.
And that kind of brings us full circle. We've seen just how delicate this energy balance is, how it's being knocked off kilter globally, and even how we can pull the levers to change it on a small scale. So a question I want to leave you with is this. If we can learn to be energy accountants for a little patch of prairie, what's it going to take for us to truly balance the budget for the entire planet?